We're going to cover gas refrigeration today. So one thing I wanted to also mention was that if you go to the EPA website, energy.gov, I believe this is EPA, you could find where a couple years ago they started having energy standards and rating for different equipment, household equipment, air conditioning systems. And there's two terms that you should be familiar with, EER, E-E-R, and SEER. And so the energy efficiency ratio, EER, is measured as the cooling capacity in BTUs per hour, Q dot in BTUs per hour, divided by the input power, W dot in, where that input power is in units of watts. Seems like a funny unit, but what happens is this is a nice number that's not like thousands. It's in the vicinity of 5, 10, 15. Most of the time, it's between 9 or 8 and 10. And it depends on. So this is for room air conditioners. They have EER ratings. The other one is SEER. SEER is a seasonal energy efficiency ratio. It's calculated using average temperature conditions and how they may vary, where the EER for window air conditioners set at the outside air is 35, the inside air is 27 with 50% relative humidity. And you'll see this U.S. government label where manufacturers are supposed to put the labels on their equipment, so you as a homeowner, as a consumer, can look and do a relative weighting of how efficient, energy efficient this equipment is. So this is where they're supposed to put a description of the equipment. Here it says, if you barely read it, but it's central air conditioner cooling only split system. So it's not a heat pump. It's like, and then this is a company, this is just made up, XYZ Corporation model, blah, blah, blah. And then they'll have a range like least efficient to most efficient, little bar showing you, oh, this is a 13.3 unit on that seasonal energy efficiency ratio. These things keep changing, so let's take a look at what's been happening. As of 06, all residential air conditioners sold in the U.S. must have a SEER of at least 13. Used to be a SEER of 10. Now they've bumped it to 13. And if you want an Energy Star qualified central air conditioner, it has to have at least a 14. Otherwise, it's not an Energy Star. True? In the United States, that requires residential systems manufactured after 05 have a minimum of 13. So they can't manufacture in the U.S. something around a 10. Although window units are exempt from the law, so their SEERs are still around 10. Actually, they're EERs. Energy efficiency ratio is usually what they have for window units. This is off of Wikipedia. Now, this is interesting. 1 year, less than 1 year from now, right? January 1st, 2015. Split central air conditioning systems, the majority of what we have in apartments and homes around here. Split systems. You have the indoor and the outside unit, right? The condensing unit outside. Installed in the southeastern region of the United States. That's basically where it's hot and humid. And they must now have at least a 14 SEER. So you can't install it. Now, what is that region? It's Alabama, Arkansas, Delaware. Why is Delaware in it? Well, anyway, Delaware's in it, Florida, Georgia, and there's Texas. Now, split systems installed in all other states out of the southeast, that's where this is right here, and the southwest region, which I didn't describe, I deleted it, still can have a minimum of 13 SEER because, you know, the summer in northern Michigan just isn't that long. In Minnesota, it's just not that long. So they basically have it where you're going to use a lot of air conditioning, you need to have it efficient. That's what they've done. Now, as I understand, this is being challenged in the courts, so who knows if it'll get implemented. I think it will get implemented, but whether it makes it January 2015, we'll find out. Ready to move on? So let's talk about gas refrigeration or Brayton cycle run backwards. So if you take a Brayton cycle and run it backwards, you supply power to it and you can provide cooling. So you have two heat exchangers, and this one would absorb Q in and this one would reject Q out. All right? This is very uncommon. It's not common, but it's easy enough for us to analyze that we have it. Okay? So the compressor is power consuming. You do have a turbine which helps reduce the amount, so it's the compressor minus what the turbine produces, what you have to purchase for the cycle, the power purchased to run the cycle. And basically this is all for air, is the favorite gas to analyze. So, but it's always an ideal gas. So if you take a look from 1 to 2, if you want to plot it on a temperature entropy diagram, what you'll do is have two lines of constant pressure, because this line right, if you cut it right here, this is all the high pressure side, isn't it? And this is all the low pressure side. So go ahead and put two lines of constant pressure on the TS diagram it's for ideal gas. And then go ahead and out here is state 1, and you're going to compress it to 2. Now that's the highest temperature that you'll find at state 2. Put it through a heat exchanger to cool it off to state 3. And then from 3 to 4, isentropically expand it. And that's the lowest temperature at 4. True? And then from 4 up to 1, you complete the cycle. So this is Q in. This is the work in from the compressor. This is Q out. And this is the work out from the turbine. If you have some irreversibilities in the compressor, it kicks it over and the temperature at 2 is higher, and kicks it over and the temperature at 4 is higher than if it was isentropic. You can see it's a challenge to air condition something, because if you look at this temperature of 1, if you're trying to cool something, you want this Q in just in a heat exchanger, right? It looks easy to bring it in right after here in the early stages of that heat exchanger when the temperature is 4, but as it's going through the heat exchanger, it's warming up and it's getting hotter and hotter. Now it's temperature 1. So what you're cooling has to be at least this temperature. The low temperature can't be below T1. Does that make sense? It can't be below T1. Otherwise, you won't get heat to transfer out of that low temperature reservoir or low temperature reservoir, low temperature source into the working fluid. Likewise, look at his. The high temperature can't be any less than T3. This is relatively easy to transfer the heat out when the gas is really hot at T2. But as it gets closer to becoming T3, it's less of a delta T to motivate or push that heat out of the gas. And so you usually don't have a great coefficient of performance. Here's a problem, but let me do this. I have the solution here. So here's a problem with the solution. So we have a gas refrigeration cycle and a compressor pressure ratio is 4. And what I did was I'll set it all up in Excel. And so I put this as the pressure ratio up here. 100, 270 for the inlet to the compressor. And then the temperature at the turbine inlet is 315. That's specified. And the efficiencies are given some value of 82% and 85%. Determine the network input per unit mass. Make a sketch and then have your properties, so all of the states labeled, and go from 1 to 2s and then 1 to 2 because of the inefficiency of the compressor. And these are all calls right away to the Excel. That was any call in here is enthalpy is a function of temperature for air. Here's PR as a function of temperature for air, like that. So, does this look good? Look at the coefficient of performance. Not very good, 0.6. All right. Let me go ahead and, how many people solved the gas refrigeration cycle for the homework due today?
I got that. I thought it was wrong. Whatever, I just turned it in like that, but now it makes sense.
About that low?
0.6 or something like that.
Low values. Other people feel comfortable doing it? All right, very good. Because of the turbine? It's really because the T low and the T high are so close together. So that's.
The turbine, you use entropy, right? And if it's like a valve.
Yeah, so it's all enthalpy changes. So the work that the compressor consumes, if it's isotropic, is this difference. And then you divide by 0.82, and so you find it takes more work. And so you add that to 270 and just walk around the problem. It's a Brayton cycle run backwards.